Alright, so suppose you got the curve of y is equal to x squared plus 1. Now it'll look like this. So what we're going to do over here is we're going to try to use rectangles to approximate the area underneath the curve between, let's say, x equals to 0 and x is equal to 3. Now if we do something like this, for each 1 unit width, we're going to say that we're going to draw a rectangle underneath to approximate the area, because we know how to find the area of a rectangle. That's just length times width. So if we do that real quick, not going to be perfect rectangles here. Do something like this. Now how you choose to draw the rectangles is the important bit. So in this case over here, what we've done is we've selected rectangles which hit the curve on their left corner, their top left corner. And this is what we call left endpoint rectangular approximation. Or we're going to refer to this as LEP, LEP. Now if you do something like this, then to find the area of each one over here, then what you can do over here is, well, we know the height over here. This height is, well, the height is determined by what the y value, the y coordinate of this first x over here is, and we know that there's a y-intercept of 0, 1. So this means that we have a height of 1, we have a width of 1 as well. So when we calculate the area, we say that we have 1 multiplied by, well, we know there's 1 unit, but we got that from saying that we want to sub in x is equal to 1 into our function over here. Sorry, not x equals to 1, x equals to 0, sorry. Bit of a brain fart there. And over here, this is where x is equal to what? X is equal to 1. So just labeling this one over here, this is 1, 2. So when you sub x equals to 1 into this rule up here, then you can say you get 1 squared plus 1. Add, oops, the width of 1 multiplied by f of 1, or this is 2. And we also add this coordinate over here, which is 1, what is it? Well, as these sums get bigger and bigger, sometimes you don't want to do it in your head. You can just simply say that this coordinate here is actually f of 2, the function when x is equal to 2. So really what's happening here is, you can actually say this one over here is not 2. Well, I mean it is 2, but how we get this 2 over here is by subbing x is equal to 1 into our rule up here. And so we say that the area of our last rectangle here is actually 1 times f of 2. So, okay, wait, hold on a sec. That's not meant to be. Where's my black? Let's see. This one over here is not a plus. This one is a times. So just to clarify, this area of this rectangle, this one here, for example, is simply the width multiplied by the height. So this here is width times height. Okay, this is how you get the area of the area underneath the curve from x equal to 0 to x equal to 3. And if you evaluate all of this, then we're going to have, let's have a look. So this one over here, f of 0, how about this? So 1 times f of 0, which is 1, plus 1 times f of 1, which is 2. And we add 1 times f of 2. 2 squared plus 1 is 5. So we have 1 times 5. And this is all equal to 1 plus 2 plus 5, which gives you 8 square units. Okay, so remember how we said at the start, it really depends on where how you draw the rectangles. So in this case over here, we use the left corner, but you can also use the right corner. And if you do this, So let's draw our curve again over here. So we have y is equal to x squared plus 1. And if we were to use the right corner instead, then what happens is when you draw your rectangle, so I'm just going to plot from 0 to 3 again. I'm using the same width, of course, we're just comparing the two cases. In this case, you can see there's an open approximation of the area this time. Because last time, there were gaps underneath the curve. But in this case over here, the rectangles are actually going to be filling up space above the curve instead. So you actually end up with too much area. But again, this is an approximation. And for some curves, it is quite nice to use this method. In any case, if you want to find the area, it's a very similar method. So over here, you can see that we're using the right corner this time. So the height over here, this height here is actually not 1 anymore. It's actually 1 squared plus 1. So this is actually the height of f of 1, because x is equal to 1 at this point. The y value is determined by f of 1. This is 1 comma f of 1. The second coordinate is 2 comma f of 2. Kind of a similar pattern, except that the last point over here instead, this time is at 3 comma f of 3. Okay, and we can find out the area by just summing up all of our rectangles. Now the first rectangle over here, it's got a width of 1, and it's got a height of f of 1. Now a handy thing to do here is to say, we can put our width, we can factorize our width on the outside, so this is our width, and then multiply it by all of the heights summed up, because that's really what we've done last time, except instead of multiplying width with each of the different heights, all of the rectangles have the same width, so we're just going to place it on the outside, and this is just a really small shortcut you can do. So we're going to have 1 times f of 1, f of 2, and f of 3. Okay. So what do we get here? Well, f of 1 is 2. Subbing in 2 will give us, well, 2 squared plus 1. This is 5. Subbing in x is equal to 3 will give us 10. So this gives us 17 square units instead. Much more than what's actually underneath the curve, but this is how we approximate.